Okay, so what we're going to do now is we're going to talk about conservative fields and the fundamental theorem of line integrals, but we need to do a little bit of review before we get there. So the first thing I want to talk about is just the different ways that we've created or discovered so far to evaluate a line integral. One thing we've done is we've said you can evaluate a line integral along a path C using f ds, where f is a function of x and y, and s is what's called the arc length parameter. But we had talked about how there are too many variables and whatnot, so then we said, you know what, if I can get c in terms of t, and c has an x and a y to it, I could get f of x, y in terms of t, and then ds is the length of the curve, which is like the magnitude of r prime dt. So we said if you wanted to evaluate this, it would become the integral from a to b of f times the magnitude of r prime dt, which really became the integral from a to b, where a and b are t values, of f of x of t, y of t, and maybe z of t too, I'm not sure, and then times the square root of x prime squared plus y prime squared, and each of these are of t. Forgot to put my t's in here. Dt. Okay, and you could evaluate f ds. You also could integrate the integral of a vector field, okay, a line integral of a vector field where you had the integral of f dot dr that calculated work. And when you want to do that, you end up dotting f with r prime, and you get everything in terms of t. So now what can I do with this beyond these two things? Well, let's come back here for a second. And it says conservative field and the fundamental theorem of line integrals. All right. First, what's a conservative field? Well, a conservative field is the other thing we need to do a quick review of. I know that a field is conservative if a couple of things happen. If I define f as m of xy, comma n of xy, if the m de y equals the n de x, then that two-dimensional vector field is conservative. If the m de y equals the n de x. If my vector field f has three components, m, n, and p, we said that it's going to be conservative if curl equals the zero vector. So wait a second, how do I get curl? Curl is where you do gradient crossed with the vector field. In other words, when you evaluate this determinant, and it's been a while, if this thing equals the zero vector, then you can say that that's conservative. Whew, there's actually one more way that I'm going to put on top. The other reason something's conservative is if you know that f, whether it's 2D or 3D, is equal to the gradient of some potential function f. This is the one where we said, what if I took the antiderivative of the vector field, I shouldn't say the antiderivative, but if I found a function whose gradient equaled the vector field f, and just to remind you, the gradient of f is the vector df to x, df to y, df to z. Whew, that was a lot to talk about something being conservative here. So down here on number 1, it says, given I have a lowercase function f of xy equals 3xy plus 2y squared minus x, find the gradient of f and rename it f. Okay, so if I want the gradient of f, then I need df to x, comma df to y, which is going to be 3y minus 1, and df to y is going to be 3x plus 4y. and they want us to call that uppercase F. Now, I automatically know that uppercase F, the vector field F, is conservative because I got it by finding a gradient. Okay, so this is guaranteed to be conservative. Now, let's see what happens when I find the work done by a conservative field on a particle. So if I move from 0, 0 to 1, 1 along the path y equals x, I'm going to sketch that path over here for reasons. So there's 0, 0, and there's 1, 1. There's my first path. So if I want to go along that path, traveling through this vector field, okay, whatever it looks like, it's a bunch of arrows, and I want to know how much work is done, work is the new deal function. Work is the integral of f dot dr. So what we are going to do is say, all right, if I'm going along the path y equals x, I need to write that path in parametric form. If I want to parameterize a function, I can let x equal t, and then since y equals x, y would also equal t. And my x goes from 0 to 1, so my interval for t will also be 0 to 1. I got to give you a hint. A lot of times when you parameterize something yourself, your t's do go from 0 to 1 an awful lot. Okay, so I need f dot dr. Well, f dot dr is the integral of f, which is 3y minus 1. That wasn't supposed to go there. 3x plus 4y. And I'm dotting that with the derivative of r. Okay, so r is this parameterization really turned into a vector value function, so it would be tt. So my derivative of r would be 1, 1. This is supposed to be in terms of t. Uh-oh, I have x's and y's in here. So if I create t's for that, y equals t, so that's 3t minus 1. X also equals t, so that's 3t plus 4t, dotted with 1, 1. And then my integral goes from 0 to 1. So I'm going to take the integral from 0 to 1 of 3t minus 1 plus 3t plus 4t after I do that dot product, which is the integral from 0 to 1 of 10t minus 1, if I'm not mistaken. And if I integrate that, that's going to be 5t squared minus t from 0 to 1, which is 4. Okay, so the work done by the field as I move along this path is 4. Let's try another path. What if I went along y equals x squared from 0 to 1? What is going to happen then? So if I go on a different path, this path's going to be longer. So I wonder if more work happens to be going on here. Well, let's see. Making sure that it's still recording here. So this time I can still let x equal t, but then y, which is x squared, would be t squared. And x is still going from 0 to 1 because it said so. So t is still going to go from 0 to 1. So I have the integral of f, which is still what it was in the beginning. Where's f? 3y minus 1, 3x plus 4y. And now I'm going to dot it with dr, the derivative of this path, which would be 1 comma 2t. And of course, OneNote's doing that thing again where things disappear. Okay, so 1 comma 2t. And now everything needs to be in terms of t. So this is going to be 3t squared minus 1, 3t plus 4t squared, dotted with 1 comma 2t. And so if I find this dot product, I go from 0 to 1, and when I multiply 3t squared minus 1 times 1, I get, oh, I keep putting that bracket there, 3t squared minus 1 There we go. And then I'm multiplying this by that. So that's going to be plus 6t squared plus 8t cubed. And we're supposed to evaluate that from 0 to 1, but I am too lazy to do that by hand. So math 9, 0 to 1 of 3t squared minus 1 plus 6t squared plus 8t cubed dt. Look at that. We got 4 again. Now, in the interest of time, that was not a coincidence. When you go from one point to another point and the points are the same, if you are in a conservative field, the same amount of work will always be done. So if I want to go from 0, 0 to 1, 1, the same amount of work is going to be done by that vector field, by a conservative field, whether I go in a straight line, whether I come all the way up and back down, whether I go all the way out and come back, whether I make a little squiggle. Look at that. It's like a broken heart. That's so sad. Whatever I do, if I follow a path to get from 0, 0 to 1, heck, if I wanted to, I could loop back the other way and kind of do one of these. Doesn't matter. If the path goes from 0, 0 to 1, 1 in a conservative field, then the work done is going to be the same for all paths connecting those 2 points, which is a pretty important thing. And when that happens, you get to use something called the fundamental theorem of line integrals. To use the fundamental theorem of line integrals, it's just like the fundamental theorem of calculus. It says if you want to evaluate an integral, you take the antiderivative, plug in the bounds, and subtract. Well, when we're talking about line integrals, the antiderivative of a vector field is its potential function. And when we do the whole plug in the bounds and subtract, it means evaluate that potential function at the end point minus the starting point. All right, let me show you what that means for this one. So using this theorem, calculate the work done by f. Well, f, which was the vector, what was it, 3y minus 1, 3x plus 4y, was the gradient field based on f, the potential function from way back in the beginning. What the heck was that? 3xy, 2y squared minus x. 3xy, 2y squared minus x. So this lowercase f, for lack of better phrasing, is the potential function for f, kind of sort of its antiderivative. So when I want to evaluate the integral from 0 to 1 of f dot dr, what I can really do is find f of 1, 1 minus f of 0, 0. The antiderivative of f is lowercase f, and instead of evaluating from t equals 0 to t equals 1, I evaluate from where I am at t equals 1 and where I am at t equals 0. So now f of 1, 1 is going to be 3 plus 2 minus 1. F of 0, 0 is 0 plus 0 minus 0. 3 plus 2 is 5 minus 1 is 4. So that equals 4. And all the other ones were 4. So that is a snapshot of how the fundamental theorem of line integrals actually works. After some snafus with OneNote, I think we got it.